Hello, welcome back, and thanks for clicking. This is another Unarculus production. Today, we're going to be talking about everyone's favorite topic, continuity, which you actually did talk about a little bit last year in pre-calc at the very beginning of the year. So we're going to review some of that stuff and see how it starts to form and really involves the concept of limits. So let's take a look at the definition. Continuity. A function f is considered to be continuous on an interval between a and b if there are no jumps, holes, gaps, or asymptotes on that function from a to b. Okay? If the function does not hold to that definition, it's said to be discontinuous on that interval. All right, so the easiest way to talk about continuity really is the idea that you can draw whatever function it is that you want to draw without having to lift up your pen or pencil, whatever it is that you may be drawing with it or drawing it with. Okay, now inevitably we're going to get people who, do one of these. Here you go. Okay. Now, I just drew that without lifting up my pencil, whether you can see it or not. So, is that continuous? No. No, it is definitely not continuous. There's a hole here, right, in the graph. Okay, so this would be discontinuous, right? This graph is said to be discontinuous, okay, on this interval. We can say from A to B. And this graph is considered to be here continuous on A to B. All right, so there's your definition, pretty simple definition. Okay, all right, let's go on our way here. There are two types of discontinuities that you need to know about. Okay, two types of discontinuities that you need to know about. One of them is called a removable discontinuity. So a discontinuity is removable. Okay, examples of removable discontinuities, let's start with that, would be holes. Okay, holes are removable discontinuities. All right, this type of discontinuity can be removed by redefining f of c in another way. Okay, all right, and we'll take a look at that in a little while, how you would do that. All right, it's actually, I don't think the ability to redefine a function is actually on the exam in terms of holes, but you know what, we're going to look at it because it does show up in calculus and it is important. So holes, okay, if we're looking at it graphically, right, we just saw a graph that has a hole in it. There's a graph that has a hole in it, okay. This graph also is considered to have a removable discontinuity. All right, so let's say we call this point C. Okay, if we call these point C, so each one of these functions is discontinuous at the value x equals c. Each one of them is discontinuous. Now you can see, all right, from the picture how it might be possible to remove the discontinuity. The picture on the left here, the easiest way to remove the discontinuity is to figure out what this point is and then somehow fill in the hole, right? We call that spackling the hole, okay? Or patching the hole, all right? Same thing over here, except, well, we already have this point, but this point happens to be down here. We'd really like for this point to be up here because that would then spackle the hole, and then that would make this line continuous, okay? So that's the concept behind removable discontinuities and spackling the hole or patching the hole, all right? But what you need to know for now is that holes are removable discontinuities, and these two pictures represent two types of holes that you could have in your graph, okay? All right, So let's head on now to our second type of discontinuity, which is a non-removable discontinuity. Okay, there are two different types that are most often found in non-removable discontinuities. This is the one you've been doing for PTOTES, asymptotes and jumps. Okay, asymptotes and jumps. All right, jumps. Okay, you would normally find or are going to find on piecewise functions. Asymptotes, you're going to be looking for them throughout, and you should already know how to find an asymptote. All right, you've already found them before. Okay, but a non-removable discontinuity just means you are unable to redefine f of c, okay, to make f continuous. That's what we mean by a non-removable discontinuity. So the two types of discontinuities are removable and non-removable. All right, and we'll show you how exactly we notate that as we go along. We take a look at a couple of examples here coming up. Okay. All right. So just so before I go, let me just draw a picture. All right. Everybody knows what functions that have asymptotes look like. Okay. There you go. There's a function that has an asymptote. It's a vertical asymptote. Vertical asymptotes are non-removable discontinuities. All right. I should be a little bit more specific. We're talking about vertical asymptotes here. Okay. A jump looks like this, normally found on piecewise functions. Okay, and for obvious reasons, you've taken one graph and then you've jumped up to the other piece, okay, or jumped down to the other piece, depending on what the graph looks like. All right, there's a place, say x equals c, where you are jumping from one function to another. And then here has a vertical asymptote at x equals c. That's a type of non-removable discontinuity as well. Okay, all right, so let's talk about how exactly we go in search of these discontinuities. If we want to find points of discontinuity, okay, we look at the domain of the function, and those excluded points are where we'll find the discontinuities. So the question is, how do you find domain? So if we're looking at it algebraically, and that's the way we're going to look at it, to find domain algebraically, right, we set the denominator, that's denominator, sort of, okay, equal to 0, right, and that, or those values of x, will be where there are issues with our function, okay? Those values of x will be our issues with our function f of x. Those values of x will be excluded from the domain. So for example, if I had a function called 1 over x minus 1, and I just set the denominator equal to 0, I would get x equals 1. Well, the denominator can't be 0, so x can't be 1. So the domain of this function would be everything except for x equals 1. At x equals 1, there is a discontinuity. All right, there is a discontinuity. It is a non-removable, okay, infinite discontinuity. Non-removable infinite discontinuity, because you cannot fix the problem with 1 over x minus 1. There's nothing that you can do to cancel the x minus 1 in the denominator, all right? We did this last year, okay? Everybody did it when you did rational functions. You tried to cancel the whole, right? You tried to eliminate one of the discontinuities that was in the denominator, okay? We're going to review it in a minute, but you did do this last year, all right? So we would consider this a non-removable infinite discontinuity. There is a vertical asymptote at x equals 1. X equals 1 is a vertical asymptote, which makes this a non-removable discontinuity. And to be a little more specific, we can use the word infinite discontinuity. Okay? All right, so now let's go take a look at a little bit of a longer example here. Let's try to classify the discontinuities of this given function. All right, so the first thing that we need to do is we need to find the domain. So we're going to set the denominator equal to 0. And now conveniently, as is a fair amount of time in high school math, it factors. So x can't be 2 and x can't be 5. All right, so these are the two values that we're going to eliminate from our domain. X equals 2 and x equals 5. Now the question is, what kind of discontinuities are they? Right? So to figure that out, we have to go back to our original function f of x, and we have to try to factor it. Okay, we have to try to remove maybe one of the discontinuities that's in the denominator. So the bottom's already factored. We could take the x out of the numerator. Okay, if we do, I'm going to do it up here so I can have room. We get x times x squared minus 4, and then we can factor that as the difference of two squares, x minus 2 times x plus 2. Okay, now conveniently, these will cancel. That's good. So what have we done? We have removed the discontinuity at x equals 2, because our function now looks like this, minus 5. Okay, we've removed the issue at x equals 2. A minute ago, when I plugged x equals 2 in, I got 0 in the denominator, right? What I was actually getting was 0 over 0, which we all know now is indeterminate, right? Which we all know now is indeterminate from limits land, okay? So since we've removed the discontinuity at x equals 2, there is a removable whole discontinuity at x equals 2. Now, we've done nothing to fix the problem at x equals 5. If I put 5 in here, I get 5 times 7, 35 over 0. Well, that's definitely no good for a function. Okay, so this discontinuity is non-removable. This is a vertical asymptote here. So this is a non-removable infinite discontinuity at x equals 5. So there are two discontinuities here. At x equals 2, it's removable. There's a hole. At x equals 5, it's a non-removable infinite discontinuity or non-removable vertical asymptote. Okay? So you have to be able to classify now what kind of discontinuity it is with the value that you get. What's important here, and what people make the easiest mistake on, is when you take the original f of x, when you're given the original problem, you need to find the domain right from the original problem. So you have to take that denominator right off the bat from the printed page and find the domain with it. Set that equal to 0. You cannot simplify it first, then find the domain, because if you do, a lot of times what you'll do is you'll cancel out the hole, and then you won't realize that there was a hole there. So if I ask you ever to classify discontinuities, you have to look for the discontinuities right away. Figure out what the domain is from the original problem that's on the printed page. okay? Then go try to classify them, all right? It's a two-step process, okay? All right, so that's classifying discontinuities algebraically. Let's talk about something that shows up all the time in this class. It will be all over the place. You'll see it again and again and again from chapter 1 all the way to chapter 5 or 6. We're going to talk about what it means for a function to be continuous at one point, at one value, x equals c. 3 things must be true for that function to be continuous at x equals c. This is the concept of point continuity. Number 1, f of c must be defined. Okay? All right, and up here, what I'll do next to point continuity is I will draw you a picture where if f of c is not defined, we would get something that's discontinuous at c. So here's c. Right? If this is f of x, and I ask you what f of c is, you're going to say, nope, it's undefined. There's a hole there. Okay? So the function's not continuous at c because there's a hole there, right? So the first thing that has to be true is f of c has to be defined. If it's not defined, then it can't be continuous at that point. Number 2, the limit as x approaches c of f of x must exist. Okay? It must exist. Now, what does this mean? The fact that the limit of f of x as x goes to c must exist. What does that mean? It means, of course, that the limit as x goes to c from the left must equal the limit as x goes to c from the right. So you have to check and be sure. So here's a picture for number 2 where if I violate this second condition, I'll get a function that's discontinuous, okay, at x equals c. So here's c. And now what's happening? Well, is f defined at x at c? Yes, it is, right? Here's where I would stand, this value, okay? But if I go on to number 2, the limit from the left and from the right have to be equal. Well, they're not, right? Because there's a jump here. So that must mean that f can't be continuous at that point. It's just not continuous, okay? And finally, the one that's, I guess, the trickiest of the 3 that also needs to be true. Basically, what we're saying here is numbers 1 and 2 must be equal. F of c must equal the limit as x goes to c of f. All right, and let me show you here. I'll show you here a picture of that condition being violated. It's probably the least obvious of the 3. But there it is, okay? Take a look at number 1. Is f of c defined? Yes. Down here, this is where I would stand. Number 2, does the limit as x goes to c exist? Yes. From the left and from the right, I go to the same place, right? But number 3, are the 2 values that you get in steps 1 and 2 equal? No, okay? Because the limit goes to one place and you stand on another. So since this is false, the function is discontinuous. Again, remember, this is just considered a whole discontinuity because if I can move this point, I'd be good. But it is still a discontinuity. It's removable, but it's still a discontinuity. So we would say a function like this is discontinuous at x equals c. Okay? So those are the 3 things that have to be true for a function to be continuous at a point called x equals c. All right? Now to remember that, we need a little help, and we can always remember this by quoting our favorite band. Well, some of you maybe. The Jackson 5. Everybody hopefully knows the Jackson 5. Okay? Maybe from a little bit back in the day, but everybody knows this song, I would hope. Continuity, it's easy as 1, 2, 3. As simple as do, re, mi, a, b, c. 1, 2, 3, continuity. Yeah, right? Okay, so that will help us to remember that there are 3 things that have to be true for a function to be continuous at a point. All right, if you're asked whether or not a function is continuous at a point, or you want to convince me that a function is continuous at a point, you must show me that all 3 of these things are true on the given function or whatever it is that you are looking at to convince me that it is continuous at the point. If you don't show me all 3, it is wrong. On the AP exam, if you don't show them all 3, it is wrong. Okay? One of the big things that you have to understand in this course is the fact that they want to see not just that you can do the math, they want to see if you can truly understand the math. Do you understand the theory behind what it is that you are doing? All right? Or are you just trying to, take a shortcut to get to the right answer? Okay, that's not going to work. So let's take a look at this function. It's a really easy one. Is f of x continuous at x equals 2? Well, if I want to see if a function is continuous at a point, I just got finished singing about point continuity. And I know that there have to be 3 things that have to be true. The Jackson 5 taught me that, right? 3 things have to be true for this function to be continuous at x equals 2. Number 1, f of 2 must be defined. F of 2 is 4. So that's good. That works. Number 2, the limit as x goes to 2 of f must exist. So that means from the left and from the right, I go to the same place. But, it's pretty easy to look and just take 2 and plug it into this limit, and you will get 4, right? So that also is true. And then number 3 says that the 2 answers that you just got, or all the answers you get, must be equal to each other. And sure enough, they're all equal to 4. So that must be continuous at x equals 2. So the answer is yes, f is continuous at x equals 2. Okay? Again, I have to show all 3 steps to convince you that this is continuous at x equals 2. Okay? If you don't show them all, it's wrong. Okay? You can't just take a shortcut and say, well, NAR knows that the limit exists. No, that does not work. All right, let's take a look at another. Here's a piecewise function. This is a little more interesting. I want to know if f is continuous for every real number x. So I guess the first thing we really need to consider is there a chance that f of x might be discontinuous, right? Okay, because if you looked at the last one, x squared, you know that's continuous, right? So the question is, are there any points where f might be discontinuous? Well, I can spot 2 in the picture, or based on the graph or the equation that's been given to me. One of them would be the value x equals 5, right? Because if I take 5 and plug it into this top piece, I'm going to get 0 on the bottom, okay? And then there'd be a discontinuity. But, okay, so I would be looking at x equals 5, but here's the thing. 5, if I actually asked you to find f of 5 for me, 5 would go in the bottom piece, not the top piece, right? Because the bottom piece takes numbers that are bigger than or equal to 1. So x equals 5 is not something we have to worry about because 5 would never go in the top piece. It would only go in the bottom piece. All right, so that was one problem solved. Now, the other place where you have to worry about the continuity of this function is here, the change point. Okay, I call this the change point for obvious reasons, because it's where the graph is going to change from one piece to another. So it's certainly possible that when you change from one piece to another, you might jump from one graph to another. And if you jump, it's discontinuous. So the question is the function going to be continuous at the change point at x equals 1? Well, the question is, how do we figure out whether or not something is continuous at a point? Well, the Jackson 5 continuity. It's easy as 1, 2, 3. Okay? So the question is it continuous at x equals 1? Well, we can figure that out. Number 1, what is f of 1? Well, 1 goes in the bottom piece, right? Because it's equal to, you get negative 6. Number 2, what is the limit as x goes to 1 of f? Well, 1 is the change point. So I'm going to have to try from both sides, right? I can't just do it from one side. I got to work from both sides and make sure that the limit comes out to be the same. So if I try 1 from the left will be just smaller than 1, right? So we're talking about 1 from the left is this way on the number line. So numbers like 0.9, 0.99, 0.999. That would mean the 1 would go in the top piece. So that's going to be 4 over negative 4, which is negative 1. And then 1 from the right is just bigger than 1. So that number is just bigger than 1 go in the top piece. So 1 minus 7 is negative 6. So the limit from the left and from the right are not equal. So this limit does not exist. From the left and from the right, you don't go to the same place. So since condition 2 has failed, then this function is discontinuous at x equals 1. And you can go a step further. This is a jump or a non-removable jump discontinuity. Okay? It's a non-removable jump discontinuity. It's a piecewise function that the change point is where you would jump, and in fact, you do jump from one piece to another. Okay? So we would say it's not continuous. Once you find one of the 3 conditions that fail, you can tell me that it's discontinuous. Okay? But until then, you have to continue to search. All right, we're going to try one more here. Okay? Something maybe that combines a bunch of stuff we learned. So now what I want to know is what value of k will make f continuous for all real numbers. So the question is, what value of k is a number, but I don't know what it is. But I want to make f continuous for all real numbers. So the question is, what do I make k? All right. Now you can guess, but you could be guessing all day, right? We don't want to do that. We want to be a little bit more strategic or smart about it. So let's take a look at our function and see if we can analyze it a little bit. Let's do a little analysis on it. Well, let's see if we can figure out a place where it might be discontinuous. Well, if we look at this, x squared plus k, if k is a number, there's not even a denominator here. So there's no way this piece by itself would be discontinuous. Same thing with the bottom piece, 3x plus 1. No way that piece would be discontinuous. So then the question is, where might it be discontinuous? And that's here at x equals 2, the change point. So the question is it continuous at x equals 2? Well, how do we make it continuous at x equals 2? We need to figure out how to make it continuous at x equals 2 by using the 3 conditions for point continuity. What is f of 2? F of 2 goes in the bottom piece. So that's 3 times 2 plus 1. That's 7. We need to find the limit as x goes to 2 of f. That means we got to try from the left and from the right. From the left, we would go in the top piece. Okay? From the left, we plug in 2 to the top piece, right? Just smaller than 2. Now remember, x goes to 2. K is the number we're looking for. So if I take 2 and put it in the top piece for x, right? It's 2 squared plus k. So this is 4 plus k. The limit as x goes to 2 from the right of f would go in the bottom piece. So that's again going to be 7. Okay? That's again going to be 7, right? We just did it up here a minute ago. So now, what do I know? Well, for the limit as x goes to 2 to exist, then I know that the left and the right hand limits must be equal to each other. So that must mean that k must be 3. Okay, k must be 3. And sure enough, You can verify it, right? Because if you take 3 and put it in up here, 4 and 3 is 7. So now the limit from the left and the limit from the right are both 7. So the limit as x goes to 2 is 7. F of 2 is 7. And the third condition is the fact that f of 2 would have to equal the limit as x goes to 2. And sure enough, it would be as long as k is equal to 3. Okay, so if k is 3, that will make the function continuous for all real numbers. This type of problem shows up on the exam every single year. Always it shows up at least once with an opportunity for you to somehow figure out how to calculate it. Okay, all right, we're all set for today. Make sure you've answered the questions as you go. Thanks for clicking, and look forward to seeing you in the next video.